Okay, everybody, this is our first session of Introduction to Reverse Engineering, a long-awaited course with Tyler Hudak. So this is the first session, and if you have any questions or comments about the video, you can always join us on our Slack channel if you're watching this on YouTube in the future. BrakeSec.signup.team. We have a channel or a track called Malware and RE, and you can join that channel and ask questions of people, or just reach out to Tyler at SecShoggoth, SecShoggoth, I believe, on Twitter. So without further ado, please take it away, Tyler.
Awesome. So I will start sharing. See if this works. So can everybody see the PowerPoint? Of course, I can't see anybody typing in chat.
Yes, I can see the PowerPoint.
Awesome. All right. So, okay, I did something. Hold on one second. Sorry, I'm getting used to the interface. Awesome. All right. So like Brian said, welcome to the reverse engineering course, put it on through Breaking Down Security podcast. I want to thank Brian and everybody else for allowing me to do this for you. So I'll just go ahead and jump right in. So if you don't know who I am, my name is Tyler Hudak. Here's my contact information, either securityshoggoth@gmail.com or at SecShoggoth on Twitter. A little bit about me. I have been working in information security for almost 20 years now. Currently, I work as the SOC and IR team lead for a large medical institution, but throughout all my career, I've done something with malware analysis or reverse engineering or incident response. Within the last 10 years or so, I've had the opportunity of really focusing in on that. And I use reverse engineering more for going in and looking at malware to figure out what it's doing, how it's working, and how to break its encryption and things like that. Not as much with exploit development. I know some people had asked me that previously, but for the most part, it has been for malware analysis. So what is the agenda of this course? Just taking a step away from what's on the slide right here, my goal for this course for you over the next 4 or 5 weeks is going to be to learn the concepts behind reverse engineering. We're going to focus on 32-bit assembly. We'll dive into 64-bit a little bit, but fortunately, for the most part, with 32-bit assembly, everything you learn for 32-bit assembly, you can apply to 64-bit assembly as well. There are some differences, which we'll touch on every once in a while, but for the most part, you'll be okay. During this session, we're really going to focus on assembly and learning the basics of assembly, as well as the tools that you use to look at assembly, in particular disassemblers and debuggers. Now, I know some of you probably know this stuff, and so I apologize. The whole goal for this session is to really make sure that everybody is on the same level. So in the coming weeks, when we start talking about what an instruction is doing, or having you go through chunks of assembler, we won't have to worry about so that somebody doesn't know what the move command does, or the add command does, or where the multiplication assembler command puts its results. That's what we're going to cover here. At the bottom there, you can see a bit.ly link, bit.ly/break-re. This is going to take you to a Google Drive, or it should hopefully take you to a Google Drive, which I will be putting stuff throughout the course. All of the exercises we're going to do, any homework I have you do between weeks, as well as any other documents and such that we'll find useful. In fact, let me pull it up right now. Let me see here. I'm gonna try something. I'm just gonna share my entire desktop, and hopefully you guys will be able to see that without a problem. So hopefully right now you guys can see, or everybody can see my browser window, and inside of it you should see the BrakeSec RE folder with 3 folders inside. The first one I'll go into is the tools folder. We're really going to be focused on using disassemblers and debuggers during this course. The ones that I'm going to be using are IDA Pro and x64 debug or x32 debug, depending on what you want to call it. I prefer these tools. These are the tools that I'm familiar with, but if you have tools that you prefer to use, feel free to use them. I may not be able to answer questions about them, but I will try my best. But I put up a copy here of the tools here just for you, so you have those in case you don't know where to find them. There's also a docs directory where, as we go through, we'll probably get suggestions for documents or things like that, which can just help us with the analysis that we're doing and help reinforce some of the concepts that we're talking about. What you have here right now is just a cheat sheet from Lenny Zeltzer talking about some different shortcuts in IDA Pro and x64 debug and a couple other tools that may be helpful to you as we go along. And then finally, here in class 1, we have a thing of exercises that we'll go through. Hopefully we'll hit them all in the class. And then we have homework. Yes, you will have homework, and we're not going to grade you, obviously, or anything like that. But at the beginning of the next course, I will go over what this, how to get through this assignment, as it were. So let me jump back to the PowerPoint. Oh, sorry. Thought I had muted. Okay. So a couple caveats. We're going to be focusing on 32-bit Windows executables. It's really not possible for us in a span of 4 or 5 weeks, 1.5 to 2 hour sessions each week, to get through all the aspects of reverse engineering. But we're going to try to get through as much as we can. My goal here is to teach you the concepts for reverse engineering so that when you do come across something that you don't know how to do, you'll at least have those base concepts. And if you go to, let's say, another operating system, let's say you want to try to do Mac malware reversal or Android reverse engineering, those base concepts that we're going to talk about are still going to apply here and still going to work here. Now, eventually, we are going to be dealing with live malware. In this case, today, we're not going to be dealing with live malware. However, in the future, we will be. And I will let you know when we're dealing with live malware and when you're going to need to take caution. But if you haven't already, definitely for next week, make sure you set up a Windows virtual machine that is segmented off of your normal system, just so that in case you do accidentally run the malware, actually, when we do start debugging the malware and reverse engineering it, we are actually going to be running it. So you definitely don't want to be doing this on your main system.
Any specific OS you should be using there, 7 or 10 or 8?
Anything that you're comfortable with, I would recommend probably something Windows 7 or beyond. I can't guarantee that the malware that we're going to look at is going to run on something old like XP, although you may be able to. All of the tools that we're talking about should run on XP and beyond. But if you can, I would do Windows 7 at least. If you don't have a license for another version of Windows, you can go to modern.ie and download a 30 or 60-day trial of Windows from Microsoft. It's a full version of Windows that you can do with whatever you want. Okay. Now, some of these slides I'm going to go through pretty quickly, and some of the stuff we're actually going to skip entirely. The reason I'm saying this is because what we're going to go through tonight is essentially equivalent to almost a college level course in assembly, an entire semester's worth. And obviously we're not going to go through everything, and obviously we're not going to cover everything that you're going to talk about in a college course on assembler, but we're going to talk about a lot of it. We're going to, from my memory of assembler, my assembler course, which admittedly was longer ago than we're going to talk about, we covered at least about all the material here in the first half of the course. So we're going to be going through it a little quickly, but I still think hopefully we'll be able to get everything knocked down for you. But, you know, a lot of times when I talk about malware analysis and reverse engineering, I get asked, you know, what is the difference between the two? Malware analysis is the study of malware to determine its characteristics and behavior. Things like, what does it do? What risk does it pose? How can it be removed? Who does it contact, and so on. And you do this through static analysis and analyzing the characteristics, and dynamic analysis by executing it. You're not necessarily going in and looking at exactly what it's doing inside the program. And that is what reverse engineering is. Reverse engineering, specifically related to malware, is an in-depth exploration in how the malware does what it does. In malware analysis, we may see that it encrypts a file. Let's say we're dealing with ransomware, and we see that it encrypts a file. We know that it encrypted a file. With reverse engineering, we're not only going to see that it encrypted the file, we're going to see how it encrypted the file. And if we can break it, if it's using a static key or something simple like an XOR encryption algorithm, that we can then go in and break and reverse the encryption and get our files back. So, are there any questions so far? From what I can tell, we're good.
Thank you for plugging the Slack on there. That's awesome. Thank you.
Absolutely. All right. So yeah, if I jump around on screens, hopefully everybody can still see it. Let me close that. All right. Okay. Also, if the resolution on my screen is too small for you guys to see, let me know and I'll adjust it. But let's jump in to talk about the tools that we're going to use. Maybe. There we go. The first tool that we're going to use for reverse engineering is a debugger. And a debugger is a program that's going to allow us to step through a program one instruction at a time. Now, the advantage of a debugger is that not only is it going to convert the machine code that's contained within the program itself into assembler, it's going to allow us to go through that, again, one instruction at a time, as well as set breakpoints to occur at specific points in the execution. Breakpoints we can set breakpoints at specific locations. So let's say there's an address that we want malware to break on, or that we know, let me rephrase that. Let's say there is a specific address that we know that malware is going to do something interesting at, that we want to look at, but we don't want to step through the entire program to get to that. We can set a breakpoint on that address, run the program, and hopefully the malware will stop running at that point. The debugger will stop it, and then we can start looking through it. There are also other types of breakpoints, some known as memory breakpoints, where we can set a breakpoint when a specific piece of memory is accessed or written to. There are also breakpoints where we can set on segments or on, let's say, specific Windows APIs. So let's say we know that malware is going to make a specific network call. We can set a breakpoint on that network call and then just wait until the malware gets to that point, and then it'll stop. In the next session, we're going to cover breakpoints. Excuse me. We're going to cover breakpoints in much more depth. Just know that a breakpoint now is just a place that we can set to stop execution. Debuggers are also going to allow us to watch all of the aspects of the running program. So we're going to be able to see all of the memory locations within the program, what's in them, how they're being modified. We're going to be able to look at all of the CPU registers to see what instructions are telling them to do. If it's a Windows program, we can see what handles it has open, so we can see what files it has open or anything like that. In addition to that, debuggers are going to allow us to patch programs in real time. This is very powerful, especially if we come across malware that has some anti-debugging functionality into it. We can then, as we're running it, we can actually patch the programs to get around a lot of these checks. And we'll talk about that more, I think, in the next session as well, maybe the session after that. We're going to spend a lot of time talking about all the anti-debugging or the ways that malware has anti-debugging in it and how we can get around it. Now, the one that we're going to use, or that I'm going to demonstrate, the debugger, is x64 debug. The reason I like this is that it's a 32 or 64-bit debugger. It can debug either program. And if you've ever used OllyDebug or Immunity Debugger, it has a very similar user interface. So you can just jump right in from Olly or Immunity into x64 debug and get a really good feel for how it is. It has plugins. Lots of plugins have been built for it that you can add into it to extend its functionality. It has built-in scripting and an SDK, so you can extend it or automate a lot of what you do. One of the really cool things within it is called Snowman, and this is a decompiler. Now, the difference between a disassembler or a debugger and a decompiler is the disassembler or debugger is only going to take that machine code and bring it back to assembler. A decompiler is then going to take that either machine code or the assembler and convert it to a higher level language, usually looking like a C-type language. Now, obviously, it's going to be a lot easier for you to understand a program and reverse engineer it if you can see what looks like C code or something that's more symbolic than just assembler. And Snowman will do this for you. Now, my experience has been that Snowman is not the best in the world. It's better than nothing, but don't expect it to work miracles for you. Another nice thing about x64 debug is that you can visualize the flow of the code within it, within the program itself. It does this by graphing them out into blocks, and this will really help you visualize loops when we talk about that, or when the different branches within a program, as opposed to just looking through one straight line. Even better, x64 debug is constantly updated. The version that's up on the Google Drive, I think, is like maybe 4 or 5 days old. And so it is always being updated, and it is still being used. So this is what x64 debug looks like. You know what? Let me do this instead of showing you guys screens. And I'll say the slides that I have here, I will send to Brian to make sure he sends it out to everyone. So here. Hopefully you guys can see my VM. I'm just going to load up x64 debug. And I'll just load up, let's say, Notepad. Oops, that's not what I wanted to do. There we go. Okay. So right here, we have x64 debug. Hopefully everybody can see this okay. There are a couple places within x64 debug that you're going to want to know about. So first, up here on top, where I'm underlining, this is going to tell you the file that we're dealing with, its process ID, and then the current module and thread that we're in. Now, this isn't going to be important initially, but as we start looking at malware, especially packed malware, you're going to want to pay attention to at least the module that you're in. Right now, it says that we're in the module ntdll.dll. This means that we're not actually in notepad.exe yet. We're in some startup initialization code. This is going to be important because as we go farther, we're going to want to see, we're going to want to basically just skip ahead till we're back into the user code. And this is going to tell us when we're in that. All right. This whole section right here in the center, that I'm circling in orange right now. Now, this section is the code itself. This is the assembler. This is really what we're going to be looking at as we go through the debugger. On the left-hand side here, let me just change that to red, down in here, these are all the addresses of the instructions. And then right here, circling in green, these are going to be the actual instructions. On the right-hand side here, you'll see some things that are out. These are some symbols. If the program is loading a string, it could be represented there. Think of these as like hints on the right-hand side. All right. On here, on this window over here, these are all the registers. Now, I loaded up a 64-bit program, so at the very top here, we see all of these 64-bit registers. And we're going to talk about all of these different registers here in a little bit, as well as a bunch more registers down here. And then finally, with what I'm circling here in green, these are the CPU flags. And again, we're going to talk about all of these in a little bit. But this is just so you know where they are within within x64 debug. All right. And then down here in the lower left corner, this is a memory dump. And in fact, you can have 5 different memory dumps within x64 debug. We're going to use these as we go through programs to see what's being stored in memory. This is going to be actually very important for us, especially when we start talking about how to break encryption or see when files are being decrypted or when data is being decrypted. We're going to set up a lot of things within the dump just to kind of watch them go through and see what they are. You can, right now, if you right click in this area, you can see at the very bottom here, we can change how we view all of this data in a lot of different formats. So right now we're just looking at, I believe, the hex version. I can change these to be unsigned byte 8-bit numbers, and you can see how it modifies that for us. And there's a lot of different ways that we can look at this. And so we're just going to leave that there for now. And then it's kind of hard to see over here. I'm going to circle it in blue. Right here, this is the stack. And we're going to be talking extensively about the stack today, but just remember that in the lower right corner, this is where you find the stack. And there are a lot of other different places that you can see things within x64 debug. You can see up here, if we had set breakpoints, there's one that's automatically set for us. We can look at them here. We can look at the memory map. This is everything that's loaded into memory for this program. So all the DLLs that are loaded into memory for Notepad are listed right here. There are, over here, symbols. This is going to be pretty important for us at some point. Every program that gets loaded up, every DLL is going to have symbols here. And we can use that to set breakpoints on later on, which I'll show you how to do it. And again, I'm just wanting you to get a little bit familiar with the way that x64 debug looks. But we're going to jump back into this in a little while. So am I going at a good speed so far?
Yeah, I'm good with that.
Okay, I'm not seeing any questions.
Nope.
So if I'm missing them, just somebody yell at me.
Will do.
All right. So over here we've got x64 debug. Looks like, okay, good. So looking here on this slide, there are a lot of different shortcuts for x64 debug that you're going to want to know, only because you don't want to be hunting for how to do these things in various menus. I've listed out at least the common ones that I use. There's F2, which is going to set a breakpoint at the location that you're at. Typically, you'll set this on a instruction. You'll just highlight the instruction, hit F2, and you've set a breakpoint. I'm going to skip over the next 2 and then jump down to F9. If you hit F9, it's going to just start running the program. If you have not set a breakpoint, then it's just going to keep going until the program stops. So you only want to hit F9 if you have some type of breakpoint set up and you're good to go. Otherwise, especially if you're examining malware, it's just going to start running off and you're going to have to reset your VM, which you're hopefully running it on. Now, if you want to go one instruction at a time, that's when you use F7 or F8. And F7 and F8 will execute one instruction at a time so you can see them. But they each do something a little bit differently. And that they really come into play when you get to a call instruction, which is calling a function. When you get to that, if you hit F7, then the debugger will go into that function. And it will then you can start stepping the instructions within that function itself. F8 does what's called stepping over the function, meaning it will execute that function and just go to the next instruction on the line below it. So think of F8 as just completely executing the functions. Just remember that it's going to do that. It's not going to go in there. So the reason this is important to know is because if you're trying to, let's say, figure out how malware is packed, and so you're stepping through the malware and you get to a function and you don't think that this is the function that unpacks the malware, but you're wrong and you step over it, then the malware is going to keep executing and it's never going to return. So you have to be really careful when you step over things. if you hit Control plus F9, that is going to execute the current function until it hits a return statement. This is great for if you're in a function that's really long or has a lot of loops and you don't want to sit there and F7 or F8 through the entire thing. You can hit Control F9 and it will execute the entire function until it gets to the end of it. Alt F9 is pretty important as well. This kind of comes into play with what I was talking about before about paying attention to what module you're in. If you're not in the user code in your program and you're in a DLL, you can hit Alt F9 and it will execute code until it gets back to your code. Especially in malware, this is usually okay to do even when you're in malware, because once you get into a DLL, you're typically dealing with operating system code and you're not dealing with malicious code. And so you really just don't want to dig into all of the operating system code that there is. If you can send the code that you're looking at to a graph by highlighting it, hitting G, and it will graph it out for you. Alt B will view breakpoints. Control G, it will bring up a little dialog for you to go in and type in an address that you want to jump to, and so on. There's a lot more here. If you highlight a bunch of code and hit Shift F5, it will decompile it with Snowman for you. We're going to go through all of these again. You're going to start using them a lot as we start stepping through code. So just remember that this slide is here in case you need it. So that was debuggers. Now we're going to talk about disassemblers. A pure disassembler is a little bit different than a debugger. Now both of them are going to convert machine code to assembler, but a disassembler is not going to allow you to execute it. This is known as static analysis. We're going to be able to look at it without executing it. Now, why would you want to do that? Well, debuggers and disassemblers typically look at code very different ways. They analyze them and the paths within the code very differently. And disassemblers, the algorithms that they use tend to be a little bit better as to finding a lot of the hidden paths within a program, or at least in my experience, they have been. And they typically provide better visualization than debuggers. Now, some, like IDA Pro, do have a debugger built into it, although I still prefer using something like x64 debug to go in and do it. But we will use disassemblers at some point to look at the code, and you'll be able to see or get a better feel for the differences between a debugger and a disassembler and why you may want to look at one versus the other. Now, the most commonly used disassembler is IDA Pro. If you buy the commercial version of IDA Pro, which I prefer it, I highly recommend it, you will be able to disassemble programs in over 50 different processors and a number of different operating systems. So it's very useful. It stores everything in a database. The IDB file that it creates for the malware or the program that you're looking at is actually a database. The nice thing about that is once you save it, you can send it to somebody else and they'll be able to look at everything that you were doing and all the comments you put in and things like that to be able to see how you were analyzing it, and then they could do something to it and send it back to you and so on. Now, the biggest problem with IDA Pro, and anybody will tell you this, is that it is almost impossible to undo anything that you do. They have this kind of ghetto undo feature inside of it, which doesn't really undo things. So I'd recommend that if you're using IDA Pro, save often, and if you make a mistake, then just load up a previous version. IDA Pro does have scripting built into it. One of the best things about it is it has IDA Python built into it, which basically means you can use Python to go through and analyze programs, which is really great when you have to do something like decrypt a bunch of strings that are in malware. IDA Pro and IDA Python is really great for doing this. So you can go in and statically see what the strings are once they've been decrypted.
So Tyler, there's IDA Pro and there's a couple of others out there like Radar and Radar 2. How do they compare to IDA Pro? I mean, other than the fact that Radar is free.
So I'm going to admit here that I have not used Radar very much. My experience with it is it's very powerful, but it has a very high learning curve. I just haven't kind of climbed that mountain yet. In my opinion, a disassembler like IDA Pro or Binary Ninja are much more accessible for people to get into and learn. And they have a lot of the features that Radar will. However, I'm going to be honest with you, I don't know enough about Radar to be able to say what the differences between the two are.
Okay. I'm sorry, I didn't mean to put you on the spot like that.
Okay. Any other questions? I'm not seeing any, so I think we're good. So hopefully we are not, this isn't going to be too dry, but this is the part where we get into the assembler. The one thing that I want you to remember as we start talking about this is that, you know, reverse engineering is in itself a complicated subject. There's a lot to it. And I mean, we're literally looking at the instructions that are being executed on the CPU of the computer. And there are lots of little things that can happen within the CPU that you need to know about. And obviously we can't cover all of those. So because of that, we're going to really just cover the basics of everything. And as we get farther and farther into it, we'll kind of pick up a couple of these little things that you'll figure out that the CPU is doing, or side effects that happen from instructions and so on. So it looks like there may be some. All right. So let's get started. We're going to start at the very beginning, the very basics. So in computers, we have bits and bytes. A bit is the smallest thing you can have in the computer, the smallest representation of data, and that is going to be a 0 or a 1. If you have 8 bits put together, then you have a byte. If you have 2 bytes put together, you have a word. 4 bytes equal a double word, and 8 bytes equal a quad word. You may already know this, but again, just want to make sure everybody is on the same level. Now, most of the time when you're looking at assembler, you're going to see numbers represented in hexadecimal as opposed to decimal. Now, hexadecimal are base 16 numbers. They go from 0 to 9 and A through F. So 0 through 9 is 0 through 9. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And then when you get to what we would consider 16, that's represented as 10 in hexadecimal. Now, up here in the upper right corner, we can see a number here that I've represented, or a byte here. Each block is set to where you'd have 1 bit. And so you know, bytes and bits are typically represented starting at 0, being at the right side, and then going counting up as you move left. In this case, we have 1 byte because we have 8 bits in here. Now, if we would fill that in with bits, this is what it would look like. This is at the very lowest level, this is what a byte looks like. Now, each byte consists of 2 hex characters. So if we take those, we have the first 4 bytes here on the left. 1101 is, let's see, that's 13, and that which is D. On the right-hand side, this is 0110, and that is represented with 6. It becomes the number 6. And so this byte here is represented as D6, or hexadecimal D6. So there might have been a question. Nope, all right, we're good. The biggest thing to take from here is that just remember that 1 byte is 8 bits, and it's represented by 2 hexadecimal characters. There you go. Now, let's talk about registers. Registers are the smallest piece of memory that you have located within a CPU, but it's also the fastest. This is essentially memory that's located on your CPU itself. And because of that, the CPU can access it, can write to it and read from it very, very quickly. And so because of that, you typically have a small number of registers on your CPU, each of which do different things. But each register can also be segmented up into smaller and smaller pieces. So the smallest you can have is a 1 byte register, or you can reference a register by 1 byte. And this is typically done by, actually let me just do this. There we go. So on a 64-bit CPU, you have a total of 64 bits or 8 bytes. And those are typically the register name prefaced by R. So in this case over here, we have RAX, which is the RAX register, and it's 8 bytes. Now you can also represent or address 4 of those bytes, the least significant 4 bytes of those, by calling it EAX. And then from there, you can represent or address the lower 2 bytes of the EAX register by calling AX, and then you can split those 2 bytes off into AH and AL, each of which are 1 byte. Now, the reason I'm bringing this up is, as we go through and as we look at assembler, we're going to see different registers that are addressed, and you know how big the data is that it's accessing based off of its name. So if you see a register being referenced in an assembly instruction by the name EAX, you know that we're dealing with 4 bytes of data. If you see one that's AL, then we know that it is 1 byte of data, and we know where in the register that it's being referenced at. Does this make sense?
Yeah, it does to me.
Cool.
Anyone else?
Cool. I don't see anybody saying no, so I think we're good. Cool. All right. There are a lot of different registers within a CPU. Now, the ones that I'm listing out here are the 32-bit registers. If you wanted to access the 64-bit version of them, you just replace the E with an R. So instead of EAX, you'd have RAX. EBX, you'd have RBX, and so on. But there are some registers that you should know what they do. EAX is a general purpose register, meaning that it can be used for pretty much anything. However, whenever you return from a function, EAX typically will contain the return value. So if you go to a function that you don't know what it does, you can always just step over that function and then look at EAX to see what's in that register, if it's data, if it points to a memory block, or so on, and that can give you an idea for what that particular function did. EBX is a general purpose register, meaning it can be used for anything, or it's typically used for anything. ECX is another general purpose one. However, ECX is commonly used as a counter, especially in loops. So if you're familiar with like a for loop, when you typically have the counter value named I is where, or ECX is where the value for I would be stored. EDX is another general purpose data register. And then we get into ESI and EDI. ESI and EDI are typically used for memory moves or memory copies or string operations, where ESI is the source index, you get it, SI, source index, and EDI is the destination index for the memory move. And we're going to talk about all the instructions that do that later on. ESP is very important. This is the stack pointer. This points to the top of the stack, or where the top of the stack is. And this is going to get moved constantly throughout the program. And we'll look here in a couple slides as to how it gets moved around. Now, because ESP, the stack pointer, is constantly getting moved around because the stack is moving up and down all the time, you need to have kind of a base point of operations, especially when you're in a function. And that's what EBP does. EBP points to a specific place on the stack in a function, and that's used to, and you use EBP plus offsets to find local variables and parameters that were passed in. And you'll see that in a little bit again. And then finally, EIP, this is the instruction pointer. This actually points to the address of the next instruction to execute. So in other words, it's not pointing to the instruction that's executing right now, it's pointing to the next one. Malware will often, as a kind of a preview for what we'll talk about in the coming weeks, malware will often do tricks with EIP in order to kind of jump around in a program. So think about it like this. So if EIP points to the next instruction that's going to be executed, and I push EIP onto the stack and then call some instructions and then restore EIP back into the EIP instruction pointer, I'm essentially moving around the code very quickly. And some malware will do this in order to kind of get around some checks to see if you're in a debugger or in a disassembler. All right. So one question. So ESP stays put and EBP moves. It's actually the opposite. They'll both move around, but ESP is going to be moving around a lot more than EBP does. I've got some slides here in a little bit that I think will illustrate it a little bit better. If it doesn't, I'll check back just to make sure. All right.
So we had another question. It says int2d, is that the same as what you were talking about?
Maybe. So when you see int in assembler, that's an interrupt, and the value behind it is the what the interrupt is going to be doing. So there are lots of different interrupts in a CPU. I don't remember what int2d does. So I would have to look that up actually to see what that interrupt actually does to tell you what it is.
Cool.
All right. So we talked about registers. So let's talk about the CPU flags now. Now, as various instructions are executed, it's going to, the CPU needs to keep track of some type of state in order to figure out, or status or condition, in order to figure out how previous instructions worked. So it does this through a specific register called the eFlags register. And within there, each different location is a specified bit flag, which basically means different things to the CPU. There are lots of different bit flags. There are only a couple that we really care about. The first is the 0 flag. And this says if the previous instruction or the result of the previous instruction was 0. So in other words, if we subtract two numbers, we may want to know if the value was 0 or not. If the 0 flag contains 0, if the 0 flag contains 0, it means that the previous instruction was not the result of the previous instruction was not 0. If the 0 flag is set to 1, meaning true, then it means that the result of the previous instruction was 0. I know that seems counterintuitive, but you'll get it as you go on. There is the carry flag. This contains the leftmost bit after an arithmetic operation. This basically means that when, let's say, you added two really large numbers together and the register couldn't contain everything in there, and so the carry flag gets set. Sorry. There's the sign flag. It tells you whether or not what the sign of the previous operation was, whether the result was positive or negative. And then finally, the overflow flag. If the result of an operation is too large to fit in a register, the overflow flag gets set. And we'll really look more at the 0 flag as we move forward. But for the most part, just keep these in mind. We'll see these especially when we get to jumps. Okay, so we talked about the stack a little bit. Let's talk about it a little bit more. The stack is an area of memory that provides storage space for data and addresses in a program. In other words, as you move around in a program, the program is going to need some place to store things, and the stack is where it stores things at. If you recall the ESP register, that points to the very top of the stack. The stack itself is a last in, first out structure. So in other words, you can kind of think of the stack as a stack of plates. As you add a plate on, the stack will grow up. When you take a plate off of the top of it, it's going to go down. Excuse me. The stack actually, this is a little confusing, but the stack grows downward from high addresses to low addresses. So you can see here on the right-hand side that at the very top of the stack, just for illustration here, I have it starting at address 0 and then going down, down, down all the way to the bottom to FFFF. Now, the stack is going to grow up, but it's going to be going down in addresses. This probably sounds confusing, but wait until the next slide and it'll make more sense then. There are two operations that really work with the stack. The first is push. This is when you're putting data onto the stack. What happens is when you push data onto the stack, the ESP is adjusted. So the ESP is moved downward, or the stack is grown, and the value is copied on. Or you can pop a value off, which means that you're going to copy the value off, and then you're going to adjust the stack pointer. Endianness. So what do you mean by that, Brian?
Well, you said as the stack grows, the address is decrement. I didn't know if that was depending on the architecture or the Indianness of the, I still don't understand the Indianness myself, so I was just wondering if that's what it was.
So Endianness, for those who don't know, that's how numbers are basically stored in memory. I'm hoping I'm getting this right, but little endian is how Intel CPUs do it. And essentially what it means is the numbers are stored in reverse order. We'll actually see that, I think, next week. Big endian means that they're stored in the order that they're specified. If you don't understand what I mean by that, don't worry. I will make sure that I have a really good example of that next week. But I don't believe that's why it grows downward. I think it is an architecture thing, but I don't think it has anything to do with endianness, although I could be very wrong about that.
Okay, thank you.
So let's look at an example just so I think it'll make a little bit more sense how the stack works. So on the left-hand side here, let's say we have these instructions. If you don't know what these instructions are, don't worry, we're going to go over them. But right now we have the stack pointer, ESP, pointing to address 28. And you can see that we already have data in the stack. At 28, we have hex CAFE. At address 2C on the stack, we have hex 1234, and so on. Above it, there will be values there at address 20 and 24, but we don't care about it right now. So the first instruction is going to move FFFF into the register EAX. Again, if you don't understand why it's specified like that, don't worry, we're going to go over that. But just know that this first instruction is putting the value FFFF into EAX. The next instruction is going to push something onto the stack. It's going to push the value of EAX onto the stack. So what you're going to see happen is ESP, the stack pointer, is going to get moved up. The stack is going to grow. Remember, it grows downward in addresses. And then the value of EAX, FFFF, is going to get pushed onto the stack. So that's what we see here. This is before, where ESP is pointing to hex 28. We push something on the stack. First, the stack grows. And then the value gets copied into the stack. Now, the next instruction is a pop instruction, meaning that it's going to pop the value at the stack, at the top of the stack, and put it into that location. So in other words, we have pop EBX. The value of whatever the stack is pointing to, in this case, FFFF, is going to get put into the EBX register, and then the stack will get decremented. It will grow down in size. It'll shrink. And, oops, sorry, went the wrong way. And that's what we see here. You can see we did a pop, the stack grew or shrunk, and the value got copied down. Now the next one, we have pop ECX. That's the next instruction. So what's going to happen here is the stack is going to take the value of where it's at right now, which is CAFE. It's going to copy it into ECX because that's the instruction that's mentioned in the pop instruction, and then the stack will be shrunk. And that's what happens here. The stack goes down. Remember, ESP is pointing to the top of the stack, so the stack shrunk, and the value that was at the top of the stack previously got copied into ECX. Now, the last one, we have a push instruction. So remember, with the push instruction, we're growing the stack. So that means that the stack is going to grow first. It's going to go back up to hex 28, or point to the value hex 28, that address. And then the value of EAX, which is FFFF, is going to get copied into that location. And that's what happens there. Does this make more sense as to how the stack works, especially with pushes and pops?
Yeah, that makes sense.
Cool. Now, if it doesn't, don't worry about that because Again, these are concepts that, college students take weeks to get through. So we're kind of go through it very fast. So somebody asked, so the pop doesn't delete anything, just overwrite it. Correct. When the stack moves up and down, it doesn't modify any of the any data on the stack unless it needs to. So when we pop a value off the stack, that value is going to stay on the stack. It's not going to leave it until we overwrite it at some point in time, if we ever overwrite it. It may never be overwritten. Okay. All right. So any more questions? The base pointer, we're going to talk about that in a second. In fact, I think that may be the next slide. Nope, not next slide. You know what? Let me just jump down to the base pointer. That's kind of far ahead, and people are asking about it. It's around here somewhere. All right. So what's the deal with the base pointer? So the base pointer is used as a fixed point in the stack for a function. So it's going to be pointing to somewhere on the stack. Remember, the ESP, the stack pointer, which points to the top of the stack, is going to be moving up and down constantly. And so when you get into a function, you're actually going to need to know where that previous function ended. Because we're kind of jumping a little bit ahead of ourselves, but when you call a function, one of the last things you do, is you push the return address onto the stack. So you need to have a fixed location as to where that place is. And that's what EBP is used for. The offsets from the EBP pointer allow you to know where the parameters are and where the local variables are. Essentially, when you look at a disassembler or a debugger, if you see a value specified as EBP minus something, so EBP minus 4, minus 8, minus C, so on, those are local variables. If you see a value EBP plus something, so like we have here, EBP plus 4 will always be the return address. EBP plus 8 and so on will be parameters that were pushed onto the stack prior to the function being called. The EBP value is always will always point to a location on the stack of the previous EBP value. So when we talk about how functions end, one of the things that's going to happen when a function ends is the previous EBP value is going to be restored. And we'll see that here at some point as we get through more and more of the instructions. Does that make a little bit more sense as to what EBP does? So when we first jump into a function, where we see EBP here, ESP, the stack pointer, will also be pointing to there. But then the stack pointer will start to move up and down as we go through. Now, this is kind of getting a little bit outside of it. Let me jump back a little bit to the stack, because I want to illustrate one thing. All right. All right, so I'm going to break out of this a little bit. So hopefully you guys will be able to see this, because I want to show you guys something about why the stack is so important and why programmers and Microsoft and everybody is so dead set on protecting the stack. So let's say we have ESP pointing to this variable right here. Let's say we go into a function, okay? And ESP and EBP are pointing to right here. That means, it's not gonna let me do this, is it? Sorry, I'm like totally messing this up. All right, let me try to jump to someplace else. All right, I'm just gonna delete a whole bunch of this stuff. All right. So again, we're kind of jumping a little bit ahead of ourselves, but when we first jump into a function, ESP and EBP is going to be pointing at the previous EBP pointer, okay? And right below that is going to be the return address. So in other words, this is going to be the function, or this is going to be the address that we return to when we leave this function that we're in. So let's say we go through and we start, our function allows us to add stuff to in a local variable, and let's say it doesn't do bounds checking very well. Let's say it doesn't. It is susceptible to a buffer overflow. And let's say our local variable is right here, which local variables will be, remember local variables are something minus the EBP. So let me just do this, just so this is where EBP will be pointing to. We have a return address here. We have, let's say, a parameter over here. We have local variable here and local variable here that we're allowed to write into. And remember, so let's pretend that this local variable right here that's stored at hex 20 is supposed to be a string, but we're not doing any bounds checking. And I add in a whole bunch of A's. So I add 4 A's here. All right, great, works. I add another 4 A's and it goes on into this value. Because remember the stack is just one contiguous piece of memory. But let's say I continue writing A's and I write another 4 A's. Now I've just overwritten the previous EBP. And if I go a little bit farther and write some more A's, I've now overwritten the return address. And this is essentially how a buffer overflow works. You get a local variable that's not doing bounds checking, and it allows me to overwrite the return address. So what will happen is, if this function completes and gets to the return, it's now going to try to return to this value, AAAA, which obviously doesn't exist, and it's going to crash my program, and then I'm going to know, hey, there's a buffer overflow in here. However, if I'm a clever exploit developer, then I can go in and change this AAAA to, let's say, 0020, which means that it will execute up here, and then I'll just put executable code in here, and then it starts to execute what I want. This is essentially a byproduct of the way that the stack grows. Remember, since it grows downward in addresses, when you start writing data into the stack, it's going to write from lowest to highest. So there's this weird thing that happens, which allows a buffer overflow to occur. That makes sense? Or did I just confuse everyone with my little tangent here? Not seeing anybody say no, so I think we're good. Cool. So with that, let's jump into the instructions. So when you look at instructions, they are going to have one or two operands, at least with x86 assembler. You're going to have operands or instructions which have either 0 operands, which have 1 operand or 2 operands. Now, those operands, in other words, the parameters to the instruction, can be different types of values. First is a register operand. You can have a register specified there, which means that the value that's going to be manipulated or read is located in that register. So here we have a move instruction, move EAX, EBX. This is an example of a register instruction. The values being manipulated are within the registers. You can have an immediate operand. This is a constant value. So in this case, we have sub ECX, 0x1. 0x1 is the immediate operand. It's just a constant value. It's essentially just a number, and it's often specified in hexadecimal. You have direct memory operands. Now, these are often specified with brackets around them, and that means that you're going to fetch the data from the specified memory location. If you're familiar with programming, this is essentially a pointer. So in this case, we have move EBX, this memory location 38B0. That means that the data specified for that parameter is located in the memory location 38B0. Yes, so whoops, sorry. Thank you for Dave for bringing that up. So, and again, like Dave said, not to confuse everyone, but there are actually two different ways that you can represent assembler when you're looking at it. There's Intel syntax and there's AT&T syntax. What we're going to be looking at is Intel syntax. And the reason we're going to be looking at Intel syntax is because, well, that's what I've learned my entire life. That's what I'm familiar with. And that's what a lot of the tools will show you by default. What does that mean to you? Really nothing, except that when you're looking at instructions, it means that the first operand is going to be the destination of it. The second operand is going to be the source of it. So in other words, if we look back up at this immediate operand example, sub ECX comma 0x1, what that means is that the value is going to be stored in ECX. If we see the one above that, move EAX comma EBX, that means it's going to be copying EBX into EAX, or in other words, you can think of this as saying EAX equals EBX. Hopefully that makes sense. With AT&T syntax, it's reversed. It usually goes, the operands go source and then destination. With Intel, it's almost always going to be destination and then source, which seems counterintuitive, but it actually helps you, I think about the assembler a little bit better. So I talked about direct memory operands. This is in the brackets. This is going to show you the memory location of where something is stored. And then you also have labels, which is basically just a logical name of a memory address. It's usually a name and then followed by a colon. The assembler typically won't have that in there. You'll usually add those in your debugger or disassembler. We have those types of operands. Then we have one other is called indirect memory operands. This calculates addresses at runtime, and it's really used to allow you to implement arrays and pointers. So let me show you a simple example. Here we have the instruction move AX comma word pointer and then in brackets BX. The word pointer and then BX in brackets is the indirect memory operand. All this essentially means is that BX is going to store a memory location, and that is where the data lies. The word in the instruction, this is the size of the data. So we know that the data here is a word in size, which if you recall is 2 bytes. And then we have the location, when the location is stored within BX. So in other words, if we were to convert this to C, this would mean that the value located within the location stored in BX is going to be put into AX. You can also do what's called address displacement. This is essentially how you create arrays or lists in assembler. So here we have the instruction array and then word 50, which means that we have 50 words that are going to be located at this memory location we're going to call array. And the dupe 0 at the end just means that initialize all those words to have the value 0. Then later on, we have this instruction that says move, into EAX, copy the value located at array plus the value at ECX. So in other words, you're taking the memory location of array, adding the memory location of whatever stored in ECX, and grabbing the value there. Think of this as the base address and what you add to the base address. Or in other words, if you're familiar with C, this is essentially an offset into an array. So the C equivalent would be we have an integer with an array of 50 integers, and at some point we say take array, take the offset of ECX into array, and then copy it into EAX. Did I just confuse everyone, or are we good with that? Because we're going to see this a lot. I want to make sure that this kind of makes sense.
Well, to be honest, I may have to run through the video a few times, but I'll pick it up.
Cool. I think as we start to get into some examples, at some point we'll start seeing it better. Just remember that when you see something like this, when you see something in brackets, that means that it's going to be manipulating memory somewhere, and that the location within the brackets contains where that memory is, or where the data is in memory. All right. All right, let's keep going. So now we're going to get into all instructions. And I'm not going to go over every single instruction because there's literally hundreds, if not thousands, of assembler instructions. I'm just going to pick and choose some interesting ones that we really care about so we can start getting into some of the examples. The one that you'll probably see the most is move. And this will copy the value of that's in operand 2 into operand 1. So if we have the example, move EAX comma 0xFFFF, this is the same as saying EAX is equal to 0xFFFF. I'm going to skip down to the very bottom to the LEA instruction. And what this means is you'll have LEA, then a register followed by a memory location. And all this means is put the address of the memory location into the register. So in other words, load address into that register. So here we have the example, LEA ESI comma string, where string is some memory location. This is essentially the same of in C code saying that we have a character array called string, and we're just copying the location that string is at into ESI in this case. The reason that you do this, by the way, that you'll see the LEA command used a lot is because a lot of instructions cannot write to memory directly. They have to write into registers, and then then there's another command that copies the value in the register back into memory. Especially things like arithmetic operations, they can't write directly to memory because it's too slow. And so oftentimes you'll see something, the LEA command used to load memory into a register, the register being manipulated, and then it being written back out. So speaking of arithmetic operations, we'll start going through those. So there's the add operation, and this takes the two operands, op1 and op2, adds them together and puts the sum in op1. It's pretty simple. Sub, for subtract, it does the same thing. It takes op1 and op2, the difference of them, and places the difference in op1. So the thing to remember with the add and subtract instructions is that it's overwriting the value that's in the first operand. Multiply will actually only take one operand. It will take the value that's already in the EAX or the AX or the AL register, multiply it by the operand, and then places the result in EDX colon EAX. So in other words, what it's doing is after it multiplies the two values together, because you may get a value that's much larger than one register, it splits them off into two registers, where the first 4 bytes will be in EAX, and then the second 4 bytes will be in EDX. The difference between mul and imul is that the mul command is only for unsigned mathematics. Imul is for signed mathematics or multiplication. Same thing happens with div and idiv. It only takes one value. It will divide the value that's already in EAX or EX by op1, and then it puts the quotient into EAX and the remainder into EDX. And then we have the neg operation, which just reverses the sign of op1. So with that, I know we've gone through a lot. Let's go through our first exercise. So we've got some assembler here, and this should actually be in the Google Drive as well. We have a bunch of assembler here. Try to walk through it by hand and figure out what the contents of my list is going to be at the very end of these instructions. Remember, my list is just going to be an array of three numbers that are word sizes. In this particular case, they're all going to be initialized to 0. But using everything that we talked about, you should be able to figure out what is going to be at the very end of this. So what I'll do is, if you want to take, let's say 10 minutes, what time is it? Yeah, why don't we take like 5 or 10 minutes and see if you can walk through it by hand and figure it out from there. If you'd like, like I said, on the Google Drive, there is like a text representation of this, so you don't have to try to copy it out by hand. And I'll be watching the chat to see if anybody has any questions.
Cool. So what I'm going to do is I'm going to pause the video, and then when we go back to explain the exercise, people will be able to follow along. So
okay, cool.
if you're working through this on YouTube, you may want to pause it now. All right, we're recording again. So this is the answers to the exercise.
All right, so recall that the goal of this was just to go through the assembler and figure out what the values in my list are going to be. So instead of doing this by hand, which we can very easily do, so we can see how our tools work, let's do it in a debugger. So on the Google Drive, let me move this over. On the Google Drive, you should have, well, one second, there we go. You guys should be able to see it now. There should also be an example1.exe, and this is just the same assembler that we saw that is in executable format. And all I've done here is I've loaded it into x64 debug, or more specifically x32 debug, because it's a 32-bit program. If you try to load it into x64 debug, it's going to error on you. Now, initially, you may look at this assembler that we have right here, this assembler right here, and think, well, this is not the same assembler as what we were just looking at in the PowerPoint slide. And you would be correct. And that's because if you look on the very top, you can see we are not in the program. We are in ntdll.dll, a DLL file. The reason that is because there are ways for programs to execute code before it gets to the first instruction within the program. And some malware will do that in order to get around debuggers and disassemblers and all that fun stuff. And so x64 debug will actually start you at the very first location that you can go to, which is within ntdll.dll, which is not what we want. So what you do here, let me see if I can get out of the markup. There we go. What you do here is we want to execute to user code. So if you remember, that is the Alt F9 command, or somewhere in here. This is why I like using the shortcuts instead, because you can find them. Run to user code. So if you go to the debug menu, then go down to run to user code, that and select that. That should do it. And here we get to it right here. This should look very similar to the code that we saw before. It may not look exact because if you look on our code, you can see that I had my list here and LEA EBX comma my list. Whereas in the debugger, because it's actually running it, my list has been replaced by this exercise_1.402.000. All that means is that's the memory location of where my list is. So remember, what we want to do is we want to see what the value at the end of our execution of code is. And so what we want to do is watch to see what gets put into this memory location here. And the way that we can do that within x64 debug, or our debugger, is right-click on this, go down to, where is it? Follow in dump, and then select what we want to follow in the dump. And in this case, we want to select 0x402.000, and because that's where our list is, that's where our array is. And you can see down here in the lower left corner in the dump, it's now changed to show us the dump itself. On the left-hand side, we have the address here, 402.000. Right now, it's just initialized with zeros. And then on the right-hand side here, it's the ASCII equivalent. They're just dots because they're zeros. Okay. So first thing that happens is we have a move instruction where it's going to move the location 402.000 into EBX. Now we know that it's moving the actual memory location itself as opposed to the data located within that memory location, because the exercise_1.402.000 is not in brackets. Because it's not in brackets, it means that it's going to copy the memory location in. So if we watch EBX right over here, this should change to 402.000. I'm just going to hit F8 so that I step one instruction and it'll execute. And we can see that's what happened. The value 402.000 was copied into EBX, and then we moved on to our next instruction. Excuse me, x64 debug is nice in that over here it tells us, you know, where the instruction pointer is pointing to. I'm not going to lie to you. I'm not sure why EDX is pointed to 401.000, but you know, if any registers are pointing to a memory location over here, they'll show it to you. Down here we have the stack, but nothing has been pushed or popped onto the stack, so nothing has happened to it. All right, so now we get to our next value. It's telling us that it wants to add the value of 5 right over here to the value that's located in the memory location specified by EBX. So we know that EBX is pointing to the top of our array, 402,000, which is down here, and this instruction is going to add 5 to it. So when I step through this, we should see 5 being added to down here, to this memory location down here, which is our first value in our array. And that's what happens. Right here, we see the value of 5. This is how long our memory location is, because remember, integers are 4 bytes long, and so that's what happened there. The next instruction is going to add 4 to EBX. So because I want you guys to, I'm going to try to make this a little interactive. I don't know if it will be, but we'll see how well this works. Where is it going to be adding that 4 to? Is it going to be adding the value of 4 to the value that's stored in the memory location specified by EBX, or to the value within EBX itself? Go ahead and type it into the chat. Okay, Chris thinks that it's going to be the value of what's stored in EBX. Dave thinks that it's the value in EBX. See if anybody else posts. All right, so we have one pointing to either. And Dave is right. What's going to happen here, because EBX is not specified in the square brackets, the value of 4 is going to be added to what's in EBX. So essentially what it's doing, like Dave said, he's correct, we're moving to the next element in our array, because each element in our array is 4 bytes long. We knew that because they're words. We saw that we saw in the PowerPoint that we created them as word, to be the size of words, which are 4 bytes. And so when I step into this, we see that the value over here, one second. The value of EBX went up by 4, but nothing changed in the memory location itself. And again, this is because the value of EBX was not in square brackets. If it was in square brackets, then it would have been taking the memory location specified by EBX and modifying it. Hopefully this is making sense. All right. So the next one we have move EAX comma 2. So in other words, this is going to copy the value of 2 into EAX. EAX is this really long value up here. So when I hit F8, step through this instruction, we see that the value of EAX was changed to 2. Now, you'll notice one thing, and I think somebody may have kind of alluded to this earlier in the chat. The value of EBX had this value in there that was pointing to some memory location somewhere. Unless the program saves that value onto the stack or into memory somewhere, that value is now lost. There's no way to get it back. So the values on the register, unless they're saved, once you overwrite them, they're gone. Actually, it's the same with any value in memory or any value on the stack. Unless you save them somewhere else, they're gone once you overwrite them. So we moved the value of 2 into EAX. Now we're going to move the value of 4 into ECX. You can see that ECX over here changed to 4. And now we have multiply ECX. Now, if you remember, the multiply command, it takes the value that's in EAX, multiplies it by the value that's specified here, ECX, and then stores it into EDX:EAX. So we have the value of 4. If we're going to try to predict what's going to happen here, we have the value of 4, which is stored in ECX, multiplied by the value of 2, which is in EAX. That gives us 8. That means that 8 should be copied into EAX, and then EDX will be cleared out because there's nothing to, the value is basically a whole bunch of zeros, 8, and it has to fill in EDX with something, and so it fills it in with zeros. So hopefully I'm correct here. When I press F8, we should see that. And we do. Cool. So we've got, like we said, we had 4 multiplied by 2, which is 8. 8 got stored into EAX, and then EDX was cleared out. Now, you may have noticed that a lot of the values, or I'm sorry, in the register, when the values change of any of the registers, or actually any of the flags as well, they change color to, at least in this case, red. That's really great to know. So as you're stepping through, you can see what registers are being modified by seeing as they change color. So in our next instruction, we have another move. It's going to move the value in the second operand, in this case EAX, into the value that's pointed by the location in EBX. So in other words, the value 8 is going to be put into the memory location specified by EAX, which is 402004, which is right here, which is our next element in our array. So we do that, and we see that indeed the value 8 was copied into 402004, which is our second array value. All right, so the next instruction will add 4 to EBX. This is moving our EBX 2 points to our next location in our array. So we added 4 to it. So we have 402008 now. And so now it's pointing to right here. And here we're going to add the value of hex 14 to this location. Again, we know it's a location because it's specified by the brackets around EBX. So hex 14 will be added to what the value in here, which is 0. So once I hit F8, we should see hex 14 go into there. And then we're at the very end. So we've stepped through all of our instructions, and we see that the value of the first value of the array is 5, the second value of the array is 8, and the last value of the array is hex 14. So let me jump back to the slide, and the contents of the slide is basically just goes through the same thing and shows us the same thing as well, just by stepping through it. Does anybody have any questions as to the instructions we just went through, or why we got what we got, or why it did anything as we went through?
Makes sense to me.
Can you go over how to zero everything out at the default in the debugger again, please? I missed that part. And
oh, okay. You know, so you mean, all right, so let me just do this. I'm going to reset it. So you mean when I went down here to follow and dump the address, why these were all zeroed out?
yes.
That is just something that the compiler did, that the debugger did. It's not something that we did specifically. Probably what happened was this 402000 is probably a data segment, and the compiler, when the program was compiled or when it started up and created that segment in memory, just went ahead and just initialized it all to zeros. It's nothing that we did ourselves.
Understood.
All right. Any other questions? Cool. Sounds like we're good. Now we just stepped through this whole list of assembly, and it really didn't do much, right? It just copied 3 values into an array. It modified and it multiplied one of those values. Nothing very big. But what we just did was reverse engineering. We went through and we figured out what this code was doing. Now, understandably, this wasn't a very complex piece of code, but the concepts that we went through are still the same. And we can extrapolate out what we did and into kind of some overarching concepts that we can go through and look at when we look at more complicated pieces of code. So the reverse engineering process itself, we can do this by hand. And in fact, we're going to do this by hand initially, because it's just a lot easier to do, and you'll start to get your mind into that mindset. But we're going to basically go through and convert the assembly into a form that allows us to understand the purpose of the code. In other words, we're going to take this assembly here that we see here, these instructions, and convert them into like the C-like pseudocode. And the way we do that is really through a three-step process. We're going to examine each instruction and convert it into a pseudocode. As we look at each instruction, we're going to be able to tell what it's doing, and we're going to write it out into some type of pseudocode. Then we're going to go through and we're going to start combining instructions and reducing instructions wherever possible and giving variables meaningful names. In other words, we're going to go through and we're going to reduce the amount of instructions we have and start combining things together as well as naming variables. And we're basically, we're basically going to do that over and over again until we can't combine and reduce any further. And at the end of that, we're going to have our like C-like code at the end, which is going to allow us to understand it a lot better. This sounds like a very repetitive process and a very cumbersome process, and it will be the first couple times we go through it. However, you're going to start finding shortcuts for yourself and starting to recognize things as you go through. So let's just go through what we just did and kind of convert it, and you'll see what I'm talking about. So the first instruction here, this mylist word pointer 3 dupe 0. We know that this means that it's creating an array of 3 integers. We know that because we have the pointer 3, or the 3 here. It tells us that it's using 3 of them, and we know that it's going to be 3 words. Now, granted, these could be 3 memory locations. These could have been 3 characters. We don't necessarily know that they were integers, but we know that they are integers just from going through and looking at the code that we did. So the first 2 instructions, when we look at them, we know that it's loading mylist into EBX, and then it's adding hex 5 into the value specified by EBX. In other words, the location of my list. So if we convert this over to the C, this means that we know that EBX is pointing to the first value in my list, and it's essentially copying the value 5 into it. So this converts over to my list sub 0 equals 0x5. The next instruction is just advancing it on, EBX on, so we know that the next time EBX is used, it's going to be looking at my list sub 1. And then we have the next 3 instructions, which are just setting up a multiplication. It's loading hex value of 2 into EAX, it's loading 4 into ECX, multiplying them out, and then storing the result of them into the value of EBX. So in other words, we have mylist:1 equals 2 times 4. And then the next instruction is just advancing EBX a little bit farther to the next value, and then it's copying the value of hex 14 into EBX. Or in other words, we have mylist sub 2 equals 0x14. So we probably skipped a bunch of steps by going through that. We could have gone through every single line and kind of converted it over to pseudocode. But in this case, this is what it essentially boils down to. These, 10 or so lines of assembly code transform into this 4 lines of this pseudo C code. And that is really what we're doing with reverse engineering. We're understanding what the assembler is doing, and we're converting it over into a higher level language. Cool. All right. So it sounds like everybody is good. It sounds like this slide actually helps a lot. So cool. I'm glad about that. The next set of instructions, we're going to go over a couple more instructions. I'm going to go through these quickly. You can look back through them later on. Just remember, again, I will be sending out these slides to everybody so you can look at them. There are shifting operations for shifting bits left and right. You'll often see these used in some type of obfuscation. You don't necessarily need to know about them now. There's bitwise math operations. So you can take 2 values and or them together, and the result will be stored in the first operand. Not is basically taking the value of the operand and flipping all the 0s to 1s and 1s to 0s. And more importantly, the one that you should really pay attention for is the XOR operation. This is going to take the value in op1 and op2, XOR them together and store them in op1. We are going to see this a lot with when we talk about encryption and finding encryption. In fact, one of the most common ways that malware will hide data or hide strings within a program is by using XOR. And so if we find a way to look through the program for XOR loops or loops that have XOR within them, chances are that's how you're going to find the at least some of the encryption that's being used. So anytime we see XOR, it's always something good to look for. Now, the one caveat to that I'll say is, whenever you XOR a value by itself, you get 0. So let's say if I took XOR EAX comma EAX, that's the same thing as setting EAX to 0. And a lot of times you'll actually see that done instead of doing something like sub EAX comma EAX. And the reason that is because the XOR instruction is actually a lot faster than the subtraction instruction. And so as a optimization, a lot of compilers will XOR two values together in order to clear them out. It doesn't necessarily mean that there's any type of encryption going on. Okay, so I ran through those quickly. Now we're going to start getting into control instructions. When we looked at the assembler here, it was really just one straight line of code, right? We went from one instruction to the next. Well, you really don't have that too often in programs. You know, you have all this branching and jumping around and calling of functions that occur within programs. And so there are very specific assembler instructions that are used to do that. So that's what we're going to talk about now. There's the jump instruction, where the operand for jump is going to contain a memory location. And it's telling the program to jump to that location. There's the call instruction, where it will have a operand, and that operand is going to be a function. Now, there are a couple things that occur when a call instruction is executed, and we'll talk about those in a little bit. It's not as simple as just jump as the jump instruction. The jump instruction just immediately moves to that location, whereas the call will set up some things. Excuse me. If you see the ret instruction, this means return. That means that it's going to be returning from a function, and some things are going to happen to the stack in order for that to happen. And we'll talk about that in a second. There is the loop instruction. The loop instruction will basically it will decrement ECX by 1. And if ECX is greater than 0, then it will jump to the location in op1. Or in the operand. If it's equal to 0, it will just continue to the next instruction. This is a very quick way for the CPU to create a very simple loop where ECX contains some type of iterator or control value. And then loop NZ and loop NE work basically the same way, but that occurs, it will loop when op1 is not 0 or the 0 flag is not set. Essentially the same as the loop instruction. So these are basically unconditional jumps, meaning that with the exception of loop, the loop commands means that it's going to be jumping to some other location. Now there are conditional jumps. Now conditional jumps are almost always preceded by the CMP, the compare instruction. And the compare instruction is going to compare two values together and then set up the CPU so that the conditional jump can check to see if it's supposed to jump. In the example here, we're comparing EAX comma 2. In other words, it's going to compare the value of EAX to the value of 2. Now, really what's going on is it's subtracting op2 from op1. In other words, in this case, it's going to take EAX and subtract 2 from it and then discard the results, but the flags get set. And this is where the flags in the CPU are the most important. Depending on which flag gets set is whether or not the conditional jump will occur. What you really need to remember is that when you see a compare, just understand that it's comparing those two values. And then the conditional jump you see next will tell you whether or not that jump gets that jump occurs. So let me show you the jumps. I think it'll make more sense that way. So we have a jump equal or jump 0 conditional jump. This is represented by JE or JZ. And so what happens is if you have the compare instruction beforehand, if the two values are equal to, then the JE conditional jump will get executed and it will jump to whatever memory address is specified. So in other words, in our previous example, we have compare EAX comma 2. What this means is that if we're using a jump if equal conditional jump, if EAX is set to the value of 2, then the jump equal will get executed. There'll be a memory address specified after that. If the two values are not equal to each other and we have the JE call here, then it will just go on to the next instruction. We have JNE or JNZ. This basically means if the two values are not equal to, they'll jump. Jump above, this means that if the first operand in the compare is greater than the second operand, then we'll jump. Jump equal or above, this is greater than or equal to. Jump below is less than, and then jump below or equal to is less than or equal to. I have the flags that are tested over here on the right-hand side. Honestly, you're not going to really need to worry about them. You'll be able to tell just by looking at the compare and then the conditional jump exactly what is going on. So, does this make sense?
Yep, absolutely.
All right. So we're going to kind of do something here a little bit, little experiment or exercise. We're actually running close to the end. So normally what I would have you do here is write some assembler code to determine if a number is even or odd. And you can do that with everything that we talked about. But instead of doing that, we'll just go over the answer so we can get to the last bit here before we're done. So if we were going to, this is how you would do it, or this is one way how you would write some assembler code to determine if a number was even or odd. We have our first line here where we have move EAX comma and then a memory location called num. We're just naming that and we're moving that into EAX. So after this is executed, the number that we want to see if it's even or odd will be in EAX. Then we're going to move 2 into EBX, and then we're going to divide, do a div EBX. Now remember, when we do the div command, the value of EAX is divided by the value specified here. So in other words, we're dividing our number by 2. And whenever you divide a number by 2, if the remainder is 0, that means we're dealing with an even number. If the remainder is not 0, it means we're dealing with an odd number. So after we do the division, remember the remainder will be stored for division command. The remainder is stored in EDX. So in the very next instruction, we compare EDX to 0. We want to see if our remainder is 0. This is a conditional jump, or we're setting up a conditional jump with the compare command. And then in the very next one, we're doing a jump 0. In other words, if the result of the previous compare is 0, then we're going to jump to the label called even. Otherwise, we're going to start executing the next command. So let's say that the value that we put in here is the number 4. If we jump to the very top, we're putting the value 4 into EAX. We're moving 2 into EBX. We're going to divide 4 by 2. And if you remember your long division, that means that we don't have a remainder. So 0 would be stored into EDX. We compare 0 to 0. And since they're equal to each other, or in other words, that the value, the jump 0 command will be true, that means we'll jump down to the even flag down here, which just db is essentially a command to define some random bytes. And so we have even number down here. If we were instead checking the value 3 at the very top here, we would move 3 into EAX. Again, we would move 2 back into EBX. We divide 3 divided by 2. And again, remembering long division, we would have now 1 within EDX, which would be the remainder. We compare 1 to 0. They're not equal to each other. or the result would not be 0. And so we would not jump to the even label. We would instead go to the next instruction, which would defines a bytes called odd number. Then we would jump to the end label, which down here has us leave the instructions. So there's a question: would it be possible to cut out lines and just compare 2 and J0 from the flag result? Compare 2. Oh, compare 2 to. Let me think about this for a second. Would it be possible to cut out lines and compare instead of pushing 2 in and using which register? Yeah, all right. So Jay, what I think Jay is asking is, could we just compare the number to 2 and instead of dividing? Is that what you're asking, Dave or Jay? So in other words, all right, so compare EAX comma 2. I see what you're saying. We could, but in that case, then we would only be comparing if the number was, if EAX was 2, as opposed to, because, so let's say, I'm trying to think of an example here. Yes, so the div command does only take registers as the operand. That's why we don't do div 0 comma, or that's why we do div EBX instead of div 0x2, because a div has to take a register. For some reason, it won't take a constant value. Okay, it looks like Jay's good. Is everybody else good? I want to make sure that I'm answering all the questions.
No, I'm good. Yep.
Cool. All right. So do we have to have 2 as move EBX comma 2? No, we don't. If we wanted to, see if a number was divisible by 3 or by 4 or by 5 or by 100, we could change the value 2 that we're moving into EBX to that value that we wanted to see if it was divisible by. Because we're looking to see if the number is even or odd, dividing it by 2 is just kind of a shortcut to do that. Cool. I think we're good. All right. So, I'm really trying to keep this to about 2 hours because I know this is a heavy subject. So I'm going to start going through things a little bit faster. There are a bunch of string commands. These are basically going to be moving values from the SI register to the DI register. And we can do that. This is where a lot of string commands are done. We're not going to worry about those now. We may see those in the future. And if we do, I will make sure that I point them out. The one thing that I will point out is with string commands, you often need to repeat these over an entire string. And in order so you don't have to write a loop command to do this, you can actually use what's called the rep command. And what this does is it will repeat the command over and over again and subtracting 1 from ECX each time until ECX is 0. So the little sample code here, we have, we're moving 10 into ECX. We move the destination string into DI, or it should actually be EDI. We're moving the source string into SI, and then we're calling rep move SB. In other words, we're going to be moving bytes, and it's going to keep doing that and subtracting 1 from ECX each time it does that until ECX is 0. So it's really just a fast way to do a loop. Then we have a bunch of other miscellaneous commands. If you've ever done anything with exploit development, you've probably seen the no-op command. It just means do nothing. Push and pop, we've already seen. Push pushes something onto the stack, pop pops something off of the stack. But then there's also push AD and pop AD. Push AD will actually take all the values in all the registers and pushes them onto a stack. Pop AD just does the opposite. It takes all the values that are on the register and pops them back into their appropriate values. Push AD and pop AD are often done with packers in order to save the state of the program. At some point, we are going to look at how to manually unpack a program. and we're going to be looking for these commands, push AD and pop AD. Because what will happen is a packer will push all the registers onto the stack using push AD right before it does the unpacking. And then just before it's done, it'll call pop AD and then jump to the unpacked code. So all we have to really do is look for the pop AD command, set a breakpoint there, and run our program. And then in theory, the unpacked program should be in memory. But we'll see that in a couple weeks. All right. So let me see here. Calling functions. We talked about the call command before. And I mentioned that when we call a function, that some things are going to happen in order to set us up into going into the program. And so now we're going to talk about what those things are. So when a function is called, the parameters are going to be pushed onto the stack. The order that they're pushed onto the stack depends on the calling convention that's being used. And I think we talk about that on the next slide. But after the parameters are pushed onto the stack, the return address, or in other words, the value of EIP, which remember points to the next location that we're going to execute, is pushed onto the stack. This is so that when we hit the return call, or the return instruction, we know that the return address that's on the stack is going to be where we're jumping back to. And then finally, we jump to the function address. Now, once that happens, we're in the function and we do what's called the function prologue. The first thing that happens is the EBP is saved onto the stack, because remember, the base pointer is that fixed point on the stack. We want to know where that's pointing to, so we want to save the previous one so we don't lose it. So the first thing that's done is it's pushed onto the stack. Then finally, ESP is copied into EBP. So this is going to, so the current point, all right, sorry. Let me start over at the function prologue. So first, EBP is pushed onto the stack so we can save it. Then ESP, which is which right now is pointing to EBP, the previous EBP, is pushed onto the stack, or I'm sorry, is copied into EBP. So essentially what we're doing here is we're taking the current top of the stack and copying it into EBP. So that's going to be our new EBP, or our new fixed point onto the stack. And then finally, ESP is subtracted to make room for local variables. So in other words, we're increasing the size of the stack, or where the top of the stack is, so that we make room for all those local variables that we want to have. Don't worry if this doesn't make sense. We'll see this over and over and over again as we go through all these functions. But just recognize that if you see down here in the middle down here where we have this decrypt pass, we have push EBP, move EBP, comma, ESP, and then sub ESP, comma, it'll be some constant value. This is called the function prologue. This means that it's setting up a function. This may be the only thing that indicates that you're dealing with a function. So if you ever see these three instructions, you know that you're dealing with the start of a function. So I mentioned that there are a number of different calling conventions that relates to how the parameters are pushed onto the stack. Well, there's at least 4 or 5 that I can think of, depending on the language you're using, depending on the compiler, and all that. The ones that you're really going to want to know about are called cdecl and standard call. And these two calling conventions handle how the parameters are passed into the function and how the stack is cleaned up when the function is left. So with cdecl, this is the standard C and C++ convention. And parameters are pushed in reverse order. In other words, the last parameter is going to be pushed first, the second to last, pushed next, and so on until the very last parameter that's pushed onto the stack is the first parameter in the function. So if we look at our example here, we have HTTP connect, or a function called HTTP connect, with the parameters URL, method, and user agent. Right below that here on the left, we have how it would look with cdecl. First, it would push user agent onto the stack, then it would push method, and then it would push URL. It's pushing these in reverse order. And then finally, it would call HTTP connect. Now the stack is cleaned up by the caller. In other words, the stack is going to be cleaned up after the function is left. And we'll see an example of that on the next slide. With standard call, this is the type of calling convention that's used for 132 API calls. In other words, if you're seeing something being called into a DLL, a function in a DLL, this is most likely the calling convention that's going to be used. Parameters are also pushed up in reversed order, right to left, just as before, so the last one is pushed first and so on. But the stack is going to be cleaned up by the called function. In other words, when the function leaves, the stack will already be in the state that it needs to be in. So let me show you right here an example. So when we leave a function, we have to remember we've done all this stuff in there. We have to restore the function. We have the old stack pointer that we have to set back up. We have the old EBP that we need to save over, and so on. And all the space that's taken up by local variables need to be cleaned up. Depending on the calling function that's being used, or the calling convention that's being used, is where will depend on how that's done. So with cdecl, the caller that is going to clean up the stack. So in other words, you'll see the function being executed, then it will return, and then in the main code, the stack will be cleaned up, and you'll see what we see up here on the top. We see the ESP being copied into EBP, EBP being popped, and so on. Now with standard call, the function itself, or what's called the callee, will clean it up. And so on the right-hand side here, we see, just in this example, for standard call in HTTP Connect, we add C to ESP because there were 3 local variables, each 4 bytes long. And so we're removing that from the stack. It calls the leave function, and it calls the leave instruction. And the leave instruction just basically restores EBP and restores the previous instruction pointer to what it needs to be, and then return is called. I know I went through that kind of fast. I probably confused a lot of people with that. Let me see if I have an example. I don't have an example. So what questions does everybody have on this? Because I know I did go through that rather quickly.
Feel free to hit us up privately or what have you.
All right, so the question, not confusing, but how does this show up in malware analysis? It really doesn't show up necessarily specifically related to malware analysis. However, it's good to know this because as you're going through and reversing a function, if you know what kind of calling convention it's using, you'll know where the parameters are being cleaned up on, and you'll know how many parameters or how big the local parameters were. This actually is helpful in figuring out, how many things are being sent to a function, which could be very useful if to know. So I'm trying to think how to rephrase this because I think I'm just babbling at the moment. So I guess when it comes down to it, how is this specifically related to malware analysis when you're reverse engineering something? It's not. It's related more to reverse engineering as a whole because it's going to allow you to help know how many local variables there are in. And not only that, it's going to help you know that if, for example, cdecl is being used as a calling convention, then when you see that add ESP comma some value after the call, you're going to know that that's related to the stack cleanup and not something that the malware itself is doing. Hopefully that makes sense. So the next question from Jay, is the stack basically the same either way, regardless of convention afterwards? Yes. If the program is working properly and the code is written properly, regardless of which convention is being used, when it's all said and done, the stack should be cleaned up appropriately afterwards, and it should be the same afterwards. Right, it's just getting a frame of reference for how it's done. So from Chris, asks, so C is one of the 3 variables, or did I miss something? Okay, so let me jump back for this one. Yeah, it's not letting me, there we go. So in this particular case, we had the HTTP connect, the function HTTP connect, that was pushing 3 values on. We're dealing with 32-bit assembler here, or we're assuming that we're dealing with 32-bit assembler here. And because we're dealing with 32-bit assembler, admittedly, I'm taking some leaps and bounds here, but I'm assuming that each of these 3 parameters are a pointer to some memory location. So in other words, these are 3 different 4-byte values, or in other words, they're a word length values. Because each of these 3 parameters are 4 bytes long, 4 plus 4 plus 4 in hex is C. So when the stack is cleaned up, that's why there's the value of C that's added to the stack. The stack is being shrunk down by, what was it, 12 bytes. Okay, cool. All right. Jumping back a little bit, we already talked about EBP. Just remember that EBP is this fixed point on the stack. And really the thing that you need to know about is anything subtracted from EBP is a local variable. Anything that's added to EBP or EBP plus something is going to be a parameter, except for EBP plus 4, which is the return address. We will see this, especially when we start looking at something in like IDA Pro. We're going to see IDA Pro is smart enough to know this. And so it's actually going to take like all of the local variables and name them as something like local 1 or something along those lines. And with all of the parameters, it's going to know that EBP plus whatever is a parameter. And so it will actually use that in order to figure out how many parameters are passed into a function. But it's always good just to remember that anything plus EBP is a parameter and anything minus EBP is a local variable. All right, so we have this exercise 3. This is just going through and reversing the function to pseudocode. I will leave that as an exercise for you guys to do on your own if you want. Just remember to go through each line and I'll just kind of step through it really fast. You'll be able to go through it on your own. Just go through each line and convert the assembler to pseudocode. Then start combining and reducing them and assigning meaningful names. In other words, if something looks like a counter, call it counter. Don't leave it as EAX because you're just going to get confused that way. And registers are constantly reused. If something looks like a total value, then call it total or something that makes sense to you. Don't just leave it as the register name or some random memory location because it's just going to confuse you. And remember, the whole point of reverse engineering is to get it to a point that you understand the code. But you just keep going and reversing it until you can't get any farther. All right, so I think this is actually a good place to stop. If you look at the syllabus, we actually weren't going to talk about loops until next week. And so I think this is actually a really good place for us to stop. When I send out the slides, feel free to go through them again. Feel free to look at all the stuff we talk about with loops. And at the very end, there is a homework. We'll save that one for next week as well. Or if you want, you can go through and do it right now. It's up in the Google Drive. Just go in there and try to figure out what the password in the program is. You can actually do this with everything that we've talked about. And I know that we've gone through a lot during these last 2 hours. It was probably a lot of really confusing concepts or complicated concepts. So please, if anybody has any questions, hit me up. either in the Slack channel or send me an email or on Twitter or any way you can get a hold of me. I'm sure some of you are smart enough to figure out how to find my phone number. I guess that's fine. Just don't do it in the middle of the night. But
Don't make it a challenge.
good point. But before I guess we stop, does anybody have any other questions or comments or concerns?
I guess that's it. Cool. Okay, so for those of you who are in the class and for those of you listening online, not every class is going to be 2 hours, right, Tyler?
No, this is definitely the longest. I think I'm going to try to keep the rest of them to at most an hour and a half.
Okay. Oh wow. Okay, so it's more than 4 CPs if you're going to be on here. So awesome. That's going to be great. So yeah, if you enjoyed this video, please tell your friends. Feel free to share them. They're on YouTube. They're for free. So please hit up the podcast if you want at BrakeSec.signup.team. Well, that's the Slack, but www.brakingsecurity.com, which is BRAKEING security.com. And you can download all of our podcasts on Google Play, iTunes, and we're also on various other applications, player.fm, TuneIn Radio, and other ones. So yeah, thanks for teaching class, Tyler, and we'll see you all again next week.